On a clear Wednesday afternoon in July of 1989, 285 passengers settled into their seats aboard United Airlines Flight 232 in Denver. 52 of them were children, flying on a promotion that let anyone under 14 travel for 1 penny. A routine trip to Chicago. 67 minutes later, every flight control on the airplane would stop responding. Over the next 44 minutes, 4 pilots would attempt something no training manual had ever described, and no simulator pilot would ever be able to repeat. It began with a single bang from the back of a DC-10. The aircraft was a McDonnell Douglas DC-10, a wide-body trijet built in 1971. It had been flying for United Airlines since the day it left the factory, 18 years, 43,000 hours in the air, nearly 17,000 takeoffs and landings. 3 General Electric CF6 engines powered the plane. 2 hung beneath the wings. The third was mounted high in the tail. And buried inside that tail engine, in a titanium fan disc spinning at thousands of revolutions per minute, there was a flaw. A microscopic pocket of nitrogen, trapped during manufacturing. It had been there since 1971. No inspection had ever caught it. The captain was Al Haynes, 57 years old, a former Marine Corps flight instructor who had joined United in 1956. He had spent 22 years as a first officer before earning his 4th stripe in 1985. By this afternoon, he had logged nearly 30,000 hours, over 7,000 of them in the DC-10. Beside him sat First Officer Bill Records, 48, who had flown for National Airlines and Pan American before coming to United. He had roughly 20,000 hours of flight time. Behind them, at the flight engineer station, was Dudley Dvorak, 51 years old, 15,000 hours of total experience. But he was new to the DC-10, just 33 hours on type. There was one more pilot on board that day, but he was not in the cockpit. Dennis Fitch, 46, was a United Airlines training captain and DC-10 check airman, sitting in first class as a passenger. He had 23,000 hours of flight time, 3,000 of them on the DC-10. He was heading home to Chicago. He had no way of knowing that within the hour, he would be kneeling on the cockpit floor between the 2 pilot seats, both hands on the throttles, trying to fly an airplane that could not be flown. If you want to know what the cockpit voice recorder captured over the next 44 minutes, please take a moment to like this video. Every like helps us reach more people with these stories. And if you have not subscribed yet, now is a good time. Back to Flight 232. Flight 232 pushed back from the gate at 2:09 p.m. Central Time. The departure was routine. The DC-10 climbed west to east across Colorado, turned north over Nebraska and into Iowa, and leveled off at 37,000 feet. In the cabin, passengers read, dozed, and the children on their penny tickets fidgeted the way children do. The crew monitored their instruments. Everything was normal. At 3:15 p.m., the aircraft was cruising over northwestern Iowa, 37,000 feet, 296 souls on board. Below them, cornfields stretched to the horizon. The fan disc in engine number 2 had now completed 15,503 cycles. The tiny nitrogen cavity that had been sealed inside the titanium since 1971 had long ago become a crack. And that crack had been growing, silently, invisibly, through every flight, every takeoff, every landing, for 18 years. It had just reached critical size. At 3:15 and 36 seconds, the crew heard it. A loud bang from the rear of the aircraft, followed by heavy vibration and shuddering through the airframe. Captain Haynes and First Officer Records checked their instruments. Engine number 2, the one mounted in the tail, had failed. Haynes called for the engine shutdown checklist. Dvorak began working through the procedure from his station, but the engine was only the beginning. Records tried to correct the aircraft's course. It had rolled into a right bank during the failure. He turned his control column to the left. Nothing happened. He pulled back. Nothing. He pushed forward. The DC-10 did not respond. Records tried full deflection in every direction. The airplane ignored him completely. He turned to Haynes. The captain took his own column and tried the same thing. Full left, full right, full forward, full back. Nothing. At the flight engineer's station, Dvorak was scanning his panels. Then he saw it. The pressure gauges for all three hydraulic systems were reading 0. Not one system, not two, all three. The DC-10 had three independent hydraulic systems, specifically designed so that no single failure could knock out more than one. But the shrapnel from the disintegrating fan disc had punched through the tail section where all three hydraulic lines ran within inches of each other. Every drop of fluid had bled out in seconds. And without hydraulic fluid, nothing moved. No ailerons, no rudder, no elevators, no spoilers, no flaps, no brakes. The airplane was now flying itself, and it was turning right, descending, with the nose slowly dropping. Haynes made a decision that no manual had ever described. He pulled the throttle on the left engine back to idle and pushed the right engine to full power. The asymmetric thrust slowly rolled the aircraft back toward wings level. It was crude, it was imprecise, but it worked. For the moment, they were still flying. At 3:20 p.m., 4 minutes after the failure, the crew radioed Minneapolis Center. They declared an emergency and requested vectors to the nearest airport. The controller gave them Sioux Gateway Airport in Sioux City, Iowa. It was about 70 miles away. Back in the cabin, Senior Flight Attendant Jan Brown heard the explosion and felt the aircraft lurch. She looked out the window and saw something no flight attendant ever trains for: a fine mist of hydraulic fluid streaming from the tail. She made her way to the cockpit. What she saw on the faces of the three pilots told her everything she needed to know. And then a message came from first class. A passenger was identifying himself as a DC-10 training captain. He was offering to help. Haynes did not hesitate. Send him up. At 3:29, Dennis Fitch stepped into the cockpit. Haynes asked him to look through the cabin windows and check whether the ailerons were moving. Fitch walked back, looked at the wings, and returned with the answer. Nothing was moving. The flight control surfaces were frozen. Fitch knelt down on the floor between the two pilot seats. Haynes asked him to take the throttles. From that position, Fitch began working the two remaining engine levers, left hand on one, right hand on the other, trying to keep the wings level and control their rate of descent. More power on the right engine turned them left. More on the left turned them right. Both engines up meant climb. Both down meant descend. The aircraft had entered a phugoid cycle, a slow, rhythmic pitching motion, nose up, nose down, nose up, nose down. With each oscillation, they lost about 1,500 feet. The plane was descending in wide, uncontrollable right-hand circles over the Iowa cornfields. They had 4 pilots, 103 years of combined experience, and not 1 minute of training for what was happening to them right now. Sioux City was still 70 miles away. For the next 30 minutes, the 4 pilots fought to keep the airplane in the air long enough to reach Sioux City. Fitch worked the throttles from his knees, adjusting power between the 2 remaining engines in tiny increments. Too much on the right, and the aircraft rolled left. Too much on the left, and it rolled right. Both up, and the nose pitched skyward. Both down, and they dropped. There was no autopilot, no trim, no way to hold a steady course. Every correction created a new problem. The aircraft descended in a series of wide right-hand circles, each one losing about 1,500 feet. From 37,000, they spiraled down through the clouds over Iowa. The phugoid cycle, that slow rocking of the nose, never stopped. The crew could dampen it, but not eliminate it. They were passengers inside their own airplane, negotiating with physics 1 throttle movement at a time. At 3:46, Fitch made a critical adjustment. He managed to coax the DC-10 into a left turn, against the aircraft's natural tendency to pull right, and lined it up in the general direction of Sioux Gateway Airport. The crew could now see the runway. Sioux City approach controller Kevin Bachman had been coordinating the emergency. He cleared the path and then radioed the crew. United 232 Heavy, the wind's currently 360 at 11, 360 at 11. You're cleared to land on any runway. Haynes laughed. Roger, you want to be particular and make it a runway, huh? It was the kind of remark only a man with 30,000 hours and nothing left to lose would make. The controller then asked the crew to make a left turn to keep them away from populated areas. Haynes responded immediately. "Whatever you do, keep us away from the city." The crew had been aiming for runway 31, the longest available strip, but the airplane would not cooperate. It drifted right and lined up instead with runway 22, a 6,600-foot strip that had been permanently closed a year earlier. Fire trucks had already been staged along runway 31. In the final minutes, they were scrambled to reposition. The airport had activated its emergency plan. On the ground, 285 Iowa Air National Guard personnel were on duty, a coincidence of scheduling that would save dozens of lives. At Marion Health Center, a shift change was underway, doubling the number of doctors and nurses available. On the flight deck, the crew lowered the landing gear using the alternate gravity drop system. The gear fell into place and locked. But nothing else changed. No flaps, no brakes, no steering on the ground. They were coming in at 220 knots, 80 knots faster than a normal landing. Their rate of descent was 1,850 feet per minute. A safe touchdown requires about 300. At 3:59, Fitch looked at the instruments and said quietly to the others, "I'll tell you what, we'll have a beer when this is all done." Haynes replied, "Well, I don't drink, but I'll sure as hell have one." At 4 p.m., the right wing dropped. Fitch slammed both throttles forward in a last attempt to level the aircraft. It was not enough. The right wingtip hit the runway first, then the right main gear. The aircraft slammed down, bounced, and the tail broke away. The fuselage slid sideways, shedding engines and landing gear. It rolled onto its back. The right wing sheared off and the fuel ignited. The main section of the aircraft cartwheeled across the runway and into a cornfield, coming to rest upside down, engulfed in fire. Of the 296 people on board, 112 were killed. 184 survived. 13 of them walked away without a scratch. And buried somewhere in a cornfield 60 miles northeast of the wreckage, the piece of metal that started all of it, the fan disc, was waiting to be found. The wreckage of Flight 232 was still burning when investigators from the National Transportation Safety Board arrived in Sioux City. The scene stretched across the airport and into the surrounding farmland. The tail section lay on one side of the runway. The cockpit, crushed almost flat, had broken away and come to rest in the grass. The main fuselage was upside down in a cornfield, blackened and hollowed out by fire. Pieces of the DC-10 were scattered across more than a mile. The cockpit voice recorder and the flight data recorder were recovered quickly. Both had survived the impact. The CVR captured the final 33 minutes and 34 seconds of the flight, beginning just after the engine failure and ending at the moment of impact. What investigators heard on that recording was not panic. It was 4 men solving an impossible problem in real time, calmly, methodically, and with an honesty that would change how the entire airline industry thought about teamwork in the cockpit. But the recorders could only tell investigators what happened inside the airplane. To understand why it happened, they needed the fan disc. The number 2 engine had disintegrated at 37,000 feet. When the Stage 1 fan disc broke apart, it sent fragments of titanium in every direction. Some of those fragments tore through the tail of the aircraft and severed the hydraulic lines. But the disc itself, the central component, the piece that would reveal the origin of the failure, had fallen out of the engine and dropped to the ground somewhere over northwestern Iowa. Somewhere in the cornfields between the aircraft's cruising position and Sioux City, a 70-pound piece of titanium was sitting in the dirt. General Electric, the engine's manufacturer, offered a $50,000 reward for the disc and $1,000 for each fan blade. Farmers across northwestern Iowa were told to watch for unusual metal objects during the fall harvest. Weeks passed. August turned to September, September turned to October, and then, on October 10th, nearly 3 months after the crash, a farmer named Janice Sorensen was harvesting corn near the town of Alta, Iowa, about 60 miles northeast of Sioux City. Her combine hit something hard beneath the soil. She climbs down to look. It was the fan disc, most of it at least, with several blades still attached, partially buried in the earth where it had fallen on July 19th. The disk was shipped to the NTSB Metallurgy Laboratory, and what they found under the microscope changed the direction of the entire investigation. There was a crack. It ran through a critical area of the disk called the bore, the thick central hub where the blades connect to the rotor. The crack had not formed in flight. It had been growing for years. Slowly, invisibly, through thousands of takeoff and landing cycles, expanding a tiny fraction with each rotation. And at the origin of that crack, investigators found something that should not have been there. A hard alpha inclusion, a small pocket of nitrogen trapped inside the titanium alloy during the manufacturing process. This was not wear. This was not metal fatigue from age. This was a defect that had been sealed inside the disk since the day it was forged. In 1971, the disk had flown for 18 years, 41,000 hours, over 15,000 cycles, and the flaw had been there from the very first flight. Investigators now had their answer, but it raised a far more troubling question. If this defect had been inside the disk for 18 years, had anyone ever looked for it? Someone had looked. That was the problem. In February 1988, 17 months before the crash, the fan disc from engine number 2 had been removed from the aircraft and sent to United Airlines engine overhaul facility in San Francisco for a routine inspection. At that point, the disc had accumulated over 14,000 cycles. The normal service life was 18,000. This was a scheduled check, part of the maintenance program designed to catch exactly the kind of defect that was now sitting on a metallurgist's table in Washington. United's inspectors examined the disc using a method called fluorescent penetrant inspection. The process involves coating the surface of the metal with a fluorescent dye, then shining ultraviolet light across it. If there is a crack on the surface, the dye seeps into it and glows under the light. It is a proven technique, but it has a limitation. It can only detect cracks that have reached the surface. In February 1988, the crack in the bore of this fan disc had not yet broken through to the surface. It was still growing beneath the metal, invisible to dye, invisible to the naked eye, but not invisible to ultrasound. General Electric had tested this same disc with ultrasound before it left the factory in 1971. That method sends sound waves into the metal and listens for echoes that bounce off internal flaws. It can see beneath the surface. GE's own engineers later testified that ultrasound could have found the crack during United's 1988 inspection. But United did not use ultrasound. They used the fluorescent dye method and found nothing. The disc was returned to service. 14 months later, it came apart at 37,000 feet. Think of it this way. Imagine you are checking a wall for water damage. You can look at the paint and see if there are stains on the surface, but the pipe behind the wall might already be cracked and leaking into the wood. You will not find that leak by looking at the paint. You need to look inside the wall. United looked at the paint. The NTSB concluded that the probable cause of the accident was the inadequate consideration given to human factors limitations in the inspection and quality control procedures used by United Airlines engine overhaul facility. In plain language, the inspection method was not good enough for the job, and no one in the process had caught that gap. But the investigation did not stop there. Because the defect itself should never have existed in the first place, the titanium alloy used to forge the disc had been produced by Tymet, a metals company in Henderson, Nevada. Tymet supplied the raw material to Alcoa, which forged it into shape. Alcoa then delivered it to General Electric for final machining and installation. During that chain of production, GE's own ultrasound testing had flagged one of the discs made from this batch as having an unsatisfactory indication. Records showed that this disc should have been scrapped. But the records were a mess. The NTSB found significant irregularities and gaps in the manufacturing documentation at GE and its suppliers. 2 rough-machined forgings with the same serial number had been routed through the system. Which one ended up in the engine was never conclusively determined. 8 fan discs had been made from the same 6,000-pound log of titanium. After the crash, when other discs from that batch were recalled and inspected, at least 2 were found to have defects similar to the one that destroyed Flight 232. The same flaw, the same titanium, sitting inside engines that were still flying passengers every day. Investigators now understood the full chain. A manufacturing defect born in 1971. an inspection that could not see it in 1988, and a catastrophic failure over Iowa in 1989. But the deepest question was still unanswered. If one disc could slip through with a hidden defect, how many others were out there? The fan disc was not the only problem. It was the trigger. But what turned an engine failure into the loss of all flight controls was something far more fundamental: the way the DC-10 was designed. The DC-10 had 3 independent hydraulic systems. Each one was powered by a different engine. The idea was simple: if one system failed, the other 2 would keep the airplane flying. It was a philosophy called redundancy, and it was the foundation of commercial aviation safety. But there was a flaw in the execution. All 3 hydraulic lines passed through the same narrow section of the tail, within inches of each other, directly in front of the number 2 engine. 3 independent systems, 1 shared pathway. And when the fan disc exploded, the shrapnel did not care which line belonged to which system. It cut through all of them at once. The NTSB pointed out that the DC-10's designers had considered the possibility of an uncontained engine failure, but they had calculated that the probability of debris severing all 3 systems simultaneously was extremely low, so low that it did not require additional protection. The numbers said it would not happen. On July 19, 1989, it happened, and Flight 232 was not the first warning. On November 9, 1973, a DC-10 operated by Overseas National Airways suffered an uncontained engine failure in its number 3 engine during takeoff from JFK. Shrapnel penetrated the fuselage and severed a hydraulic line. The crew landed safely, but the event demonstrated that engine debris could reach hydraulic components. Then, on September 22, 1981, another DC-10, this one operated by the same airline, United, had an uncontained failure of its number 2 tail engine during takeoff from San Francisco. Disc fragments penetrated the tail and damaged 2 of the 3 hydraulic systems. The crew managed to land because the 3rd system remained intact. 2 out of 3 lines were hit. The airplane survived by a single system. 8 years later, over Iowa, the 3rd system did not survive. The NTSB had been aware of this vulnerability. In their report, investigators noted that the design philosophy assumed each hydraulic system was truly independent. But physical independence means nothing if the lines are routed through the same space. The separation was on paper, not in metal. McDonnell Douglas, the manufacturer, argued that the probability calculations met the certification standards of the time, and technically, they were right. The federal regulations did not require the hydraulic lines to be physically separated at every point along the airframe. The rules allowed for shared routing as long as the statistical probability of simultaneous failure was low enough. But probability is not the same as safety. The families of 112 people learned that distinction on a runway in Iowa. After the crash, the NTSB recommended that the FAA require hydraulic fuse systems on the DC-10, devices that would automatically seal a damaged hydraulic line and prevent total fluid loss. Japan Airlines had already installed such fuses on its DC-10 fleet following its own catastrophic hydraulic failure on Japan Airlines Flight 123 in 1985, which killed 520 people. The technology existed. It simply had not been required. The investigation also examined how United Airlines maintained and inspected its engines. The fluorescent penetrant method used during the 1988 inspection was standard practice across the industry. No airline was required to use ultrasound on fan discs during routine overhauls. United had followed the rules. The rules were not enough. The system had not failed in one place. It had failed everywhere: in the foundry, in the factory, in the maintenance hangar, and in the regulations that governed all of them. And now the question was whether anything would change. It changed. In the months and years following the crash of Flight 232, the NTSB issued a series of recommendations that reshaped how jet engines are built, how they are inspected, and how airplanes are designed to survive when those engines fail. The manufacturing process for titanium rotor discs was overhauled. The double vacuum melting method that had produced the flawed disc was replaced across the industry by a triple vacuum process. an additional melting cycle at higher temperatures designed to eliminate the gas pockets that had hidden inside the Flight 232 disk for 18 years. New standards were established for every stage of production, from the raw titanium ingot to the finished rotor. A federal committee, the Jet Engine Titanium Quality Committee, was created specifically to track and report inclusions found in titanium alloy during manufacturing. The kind of defect that brought down Flight 232 would no longer pass through the system unnoticed. Inspection methods changed as well. The FAA issued airworthiness directives requiring ultrasonic inspections of CF6 fan disks, the same method that could have caught the crack during United's 1988 overhaul. The era of relying solely on surface-level fluorescent dye was over. Airlines were now required to look inside the metal. The DC-10's hydraulic system was modified. Fuse devices were installed to prevent total fluid loss in the event of a line rupture, the same technology that Japan Airlines had already adopted after its own disaster 4 years earlier. And the FAA launched a broader review of hydraulic routing on all wide-body aircraft, ensuring that redundant systems were not just independent on paper, but physically separated where it mattered most. But the legacy of Flight 232 reached beyond hardware. It changed how pilots are trained to work together. The concept was called crew resource management. It had existed in some form since the early 1980s, and United Airlines had been one of the first carriers to adopt it. The idea was simple. The captain is not the only voice in the cockpit. Every crew member has a responsibility to speak up, offer input, and challenge decisions when safety is at stake. Before CRM, the captain's word was absolute. After Flight 232, the entire industry saw what happened when 4 pilots pooled their knowledge, communicated openly, and made decisions as a team under the worst conditions imaginable. Al Haynes spent the rest of his life talking about that lesson. After recovering from his injuries, he returned to flying for United Airlines and retired in 1991. He then became a public speaker, traveling the world to share the story of Flight 232. He never accepted payment. Every dollar went to scholarships and charities, including one honoring flight attendant Renee LeBeau, who did not survive the crash. Haynes always insisted he was not a hero. He said it was luck, preparation, communication, and the people of Sioux City who deserved the credit. Dennis Fitch, the training captain who knelt between the seats and flew the throttles for 44 minutes, was the most seriously injured of the 4 pilots. He suffered multiple fractures and organ damage. He eventually recovered but never returned to the cockpit. He passed away in May of 2012. Al Haynes died on August 25, 2019, 6 days before his 88th birthday, 30 years after Sioux City. A memorial stands today at the crash site in Sioux City, honoring the 112 people who did not survive. If this story meant something to you, do me one favor. Hit that like button. One like is all it takes to tell YouTube this story matters. Subscribe and turn on the bell so you do not miss the next one. We cover the flights that changed aviation, the disasters, the heroes, the investigations that made the sky safer for everyone. Leave a comment. Tell us where you are watching from. Are you in the United States, Canada, the United Kingdom, somewhere else? Every comment builds this community, and every voice helps make sure these stories are not forgotten. 112 people lost their lives on Flight 232, but because of what investigators pulled from that cornfield, the way jet engines are built, inspected, and maintained was redesigned from the ground up. Those changes protect every person who boards a plane today. Thank you for watching, and thank you for being here.